Hi everyone! Today I'm giving a short introduction to red-black trees. Red-black trees are a type of self-balancing binary tree, often first taught about in data structures courses. Red-black trees must follow a set of rules in order to maintain balance. 1. Each node is either red or black. 2. The root is always black. 3. All null leaf nodes, known as nil nodes, are black. 4. If a node is red, then both its children are black. 5. Every path from a given node to any of its ascendant nil nodes contains the same number of black nodes. For example, let's choose the root node and begin counting the black nodes to the left and right of every path. 1, 2. As you can see, there are 2 black nodes from the root to any of its ascendant black nodes, black nil leaf nodes. If any of these rules are violated, we will need to rebalance. There are 3 cases for rebalancing. Nodes are first inserted with normal BST insertion rules and are also first inserted as red. This may violate Rule 4 because a red node cannot have a red child. Thus, in case 1, if a node's uncle is red, we recolor the parent and uncle to black, and the grandparent to red. Just a side note here, the root in this example is red, which would violate Rule 2 that the root must be black. For now, imagine this diagram as part of a larger red-black tree. Case 2. If a node is in a triangle with a black uncle, we switch, the typically more used terminology is rotate, the node with the parent. Node's parent here is 9, so we rotated 9 to the right. In case 3, remember there is a null black node to the left of the root node. Node is in a line with a black uncle node, so we rotate the grandparent with the parent. Then we recolor the parent and the grandparent. Remember to follow BST ordering property, so that the original root, which had a 6, becomes the left child of 8, the new root. In summary, here are the 3 cases for rebalancing. Case 1. If node's uncle is red, recolor the parent, uncle, and grandparent. Case 2. If node is in a triangle with a black uncle, rotate the node with parent. Case 3. If node is in a line with a black uncle node, rotate the parent with the node's grandparents, then recolor the parent and the grandparent. Red-black trees have so many rules and cases to remember. It seems so complex. Why would we use or learn about them? Well, recall that regular BSTs have OH, height, time complexity for operations like adding, deleting, and searching. In average or best cases where the BST is balanced, BSTs have O log n time complexity. However, if the BST is extremely skewed or unbalanced, BSTs would have O n time complexity for operations in the worst case. If you searched for the largest element in this tree, you would have to look at every node, which would be O n time. Red-black trees solve this issue because they are self-balancing and guarantee that height is log n. Therefore, operations should always achieve O log n time complexity, which is better than O n time. So, thank you for watching. This topic was really confusing when I learned it in class, so I made this video to understand it a little better and hopefully explain it to others who may have been confused as well. Please stay tuned for the next video in which I work out an example on a red-black tree that applies all 3 cases of insertions.